Hi, this is our submission for the Sustainable Aviation competition. We are Cambridge team and we looked into gliding drones.
We started by having a meeting where we decided what sort of area we wanted to look into, and one area which we decided drones decided drones were an area where we wanted to look into, and then we started to think about more about what kind of drones there are, what sort of drones are going to be used in the next few years. And one area which is growing and will continue to grow is delivery drones, especially as Amazon and other online retailers try to grow that area of their business, because it means they can have fast delivery times. But also they want the most energy efficient types of drones. One, for environmental reasons, and two, it's cheaper for the company to have the cheaper drone, to have a more energy efficient drone. So we decided that was the area we're going to look into. So by that, after that we decided to split off research into existing solutions, both in what Amazon and its competitors already developed in terms of the drone deliveries that they have, and in existing solutions which could make the drones more energy efficient anyway, so stuff like solar panels, stuff like new materials, new manufacturing techniques. So then once we brought back all of that, we had another meeting where we decided that a gliding drone would be the most energy efficient possible for delivering packages over long distance autonomously. And the reason why we chose that market is because there are lots of quadcopters who can do short distance deliveries inside a city, inside an urban area, but there aren't many drones which could do a longer distance delivery across a sparser area. So therefore, and obviously for that to be an energy efficient glider is the best way to do that. So that's why we looked at the gap in the current marketplace, and we thought that's where we should produce a concept to fill it.
So in terms of practical project planning and management, we used a 3D experience platform where we actually, shown in a video, like we distributed the tasks to our members, and like we did it on time, and like the platform is pretty handy because like one Gantt chart was automatically generated. And next we did a deep investigation into the existing drone design, and there are several popular existing drones used for delivery, but like by investigating into that, we find like they all have some sort of main drawbacks, which is they all have short flight time, and the load they can carry would not be too heavy. So we were thinking like we should focus on how to save energy to extend the flight time and increase the load capacity. So in order to increase the energy efficiency, so we decided to produce a gliding mode design.
For the material selection, we have a wide range of choice that is pretty much already very common in the aerospace industry. First off, we have the aluminum on the top left, and that's mainly used in frames of drones or any aircraft. So we decided that's going to be like for parts that need strength. Then we have also looked into natural fiber reinforced polymer, which is basically like hemp fiber, jute fiber, or bamboo. It's an exciting new frontier, but there are many drawbacks, especially the chemical that needs to be used to treat the fibers so that they're not inflammable, so that they are waterproof and resistant to microbacterial. So that's a lot of setback that is not very environmental friendly. And then we have glass fiber and carbon fiber composites. These are very similar in structure and in properties. However, there's an edge to the carbon fiber composite that makes it better for our drone design. And that is additive manufacturing, because the usual way that these aircrafts are produced from carbon fiber sheets is that they are layered and they are put into molds with resins, and then they are heat treated until they're set, and then the molds are split apart. It's very labor intensive. Sometimes one aircraft requires 25 craftsmen to working on it, and then they can only produce one of them a month. But for the additive manufacturing, there's more design freedom, more organic shapes can be made, and of course, like the reinforcement that goes into the aircraft is going to be specific to the area that actually need it, and that's going to contribute to reducing the weight of the whole aircraft. Another thing is repeatable. Another problem with the usual way of doing carbon fiber composite layup is that the weight varies, although not a lot, but that could be a drawback. And the most important one is there's less material waste, because there's no need to cut all the excessive carbon fiber out of the molds anymore. Yeah, it's a very quite established area of industry already. There are many companies that do produce carbon fiber reinforced extrusion polymer that can be bought and used in this sort of operation.
So as more effort is put into the renewable energy sector, integrated photovoltaics are one of the areas that it's sort of up and coming, and there's more research and effort put into it. And these are basically solar panels, photovoltaic panels that are inbuilt into buildings and vehicles, and so we're interested in the VIPV side of it. They're more appealing as they're integrated into the structure, so we wouldn't have any protrusions, meaning that the drone is aerodynamic, and it would also save on primary materials, so we'd be using less carbon fiber purely because some of the carbon fiber is offset by the solar panels, and it also means that we don't require as much material protection from weather or from the elements. The systems produce heat and electricity as well, which is obviously one of the drawbacks, but the fact that the drone will be traveling at high speeds and be surrounded by airflow means that it is always kept at a functioning temperature, not risking overheating. And so looking into the materials has allowed us to find some weight reduction using the carbon fiber. And from this, we have allowed ourselves to basically use the solar panels as a sort of primary power source, as well as a backup power source if the main batteries fail, obviously because this is long distance. And so having the solar panels on working during flight time would mean that we are constantly recharging and using solar energy. And looking into possible solar panels that we could use, we would potentially need 4 2.6 meters by 0.35 meter panels, and this would add a total weight of about 14 kilograms, which would be offset from using carbon fiber.
So this is our first concept of the drone which we drew up. So once we had done all the research, we decided that we wanted to get a feel for the scale and the size of the drone. So sort of how big the wings are going to have to be, how big the cargo hold is going to have to be, and how this all works into having it in a aerodynamic body and stuff like that. So this was sort of our first look into that. And we based so as you can see the cargo hold on the right, we based it off a Royal Mail medium-sized package. So there was lots of flexibility in terms of the size of the package, which the drone could accommodate and deliver to the customers. And then we developed that design into a new body. We left the wings the same because the wings are fairly standard, but we developed it into a new body, concentrating material where we needed it and taking it away where it was unnecessary, which I believe you did more of.
Yeah, so this design is only focusing on the fuselage, and this is done by using X shape in coordination with X design. First off, the wing attachment. This is based off a lot of the one-man glider that have detachable wings, and you can see that the hole for the spars to go through. This makes it very easy to store the whole aircraft. And then the main body, you can see the highlighted in red is the section for the packages, and like Max said, it can accommodate about 4 medium-sized parcels. At the front, this is going to contain the propeller, the motor, and the battery. And then on the top of the highlighted red, on the top of the red highlight is the wing area, and also accommodating electronics and any lowering mechanism for the packages. And the reason that the body is quite long is because of 2 reasons. Firstly, we want a better control of the aircraft as a whole, so that the rudder and the elevator can doesn't have to exert as much force in order to pitch or yaw the aircraft, because we are using the moment arm that the lengths provide. But also we can't make the body too long, because that's going to increase the drag. This design has the fineness ratio of about 7:1, so which is in the optimum area for this sort of fuselage. But the body is also hollowed inside, with exception of the end of the aircraft and a little bit at the front for reinforcement. And we can also add reinforcement into the individual panels using the additive manufacturing.
So the design of this glider drone is based on the working principle of manned gliders, utilizing their highly efficient and slow descending characteristics to make the current commercial delivery drones more sustainable and more energy efficient. So the major source of energy of this glider drone is the pockets of air, rising air, or commonly known as thermals. Although we also plan to have backup motors on board to prevent the drone falling out of the sky. To launch the drone, we can either use its own motor or by winch to get it up to a preset altitude, as indicated green here. And then we can use the autopilot software to take over and then maintain the drone in a certain range of altitude between the maximum and minimum soar altitude. So here is a little animation of how it works. First of all, we set the maximum, minimum, and the critical altitude for the software and a destination. When the drone is above the minimum altitude, you fly to soar to the destination, and once it's descend to the minimum left altitude, then it will start to soar in the thermal to regain altitude. If it fails to find any thermal, or it doesn't gain enough altitude and fall below the critical altitude, then the motor will kick in to prevent the drones falling out of the sky. But this is just a contingency plan. Even though we haven't developed such autopilot system ourselves, there is a software called Arduino Pilot that could achieve this functionality already. So we believe this design is highly feasible and would significantly reduce the carbon emission from delivery drones in the future. So here's an example of how the drone will work. So at the working altitude, the drone will circulate in thermal, and then to gain altitude. When it's gained enough altitude, it will travel to a destination. And once it needs to gain altitude, you will circle in thermals again to regain altitude.
So yeah, that's our submission for the Sustainable Aviation competition. Thank you for listening, and we look forward to hearing from you.